Thank you everyone for joining another CPPC seminar on a somewhat unusual day, even though it's our usual time slot. So thank you for the effort. It is a great pleasure to welcome Chris Allton to the University of Sydney, to our seminars and such. Chris is an Australian who I know not from here, but from random conferences. Random places and times in the last 20 years.
I wouldn't know when we first met. That's a good summary.
And he is patriotically wearing a T-shirt from the quark confinement meeting that was held in Cairns earlier in the year, when we ran into each other and discussed that he might give this seminar on the topic that you see here. So I said Chris is an Australian. He's born in Kalgoorlie, but brought up in Brisbane and was a UQ student. There are one or two people here with a UQ connection of some kind or other. And he then did his PhD at ANU with Chris Hamer, who some of us of the more grey-haired persuasion will remember. Right at the end of his PhD, as supervisors are wont to do when you're doing a PhD, got a job somewhere else. And that somewhere else was the University of New South Wales. And so he lived at Randwick for a year at the end of his PhD doing that. He's subsequently had postdocs at Edinburgh, Southampton and Rome. And from 1995, he has been in sunny Swansea in Wales, and is basically a hard, dyed-in-the-wool lattice QCD person since many years, and is going to tell us more about the strong interaction.
Great. Thank you very much, Bruce. So I hope everyone can hear me. I can't obviously see everyone remotely, but I guess I can be heard. So it's great to be back in Sydney. It was great spending a year here. It was some time ago. I had a choice of staying in Canberra or moving to Sydney. It took about half a microsecond to make the decision to move to Sydney. I've just realised
someone from ANU.
But now Canberra is so much nicer than it was back then. So here's the tourist information shots of Swansea. There's two campuses. You've seen this a while, so I'll just move on. I'm actually, obviously, it's been mentioned already, from Brisbane.
Yes, I'm a Swan supporter.
So I'll move quickly on. But I couldn't resist. Okay, so here's an overview of my talk. So I'll talk about QCD, and the word phase comes into it. So QCD phase diagram. QCD, the strong interaction, really does have phases. I'll talk about lattice gauge theory. I'll give a brief introduction. There's not so much lattice gauge theory done in Sydney and New South Wales, I guess, anymore. So I'll talk about that. I'll talk a lot about stat mech. There's a big analogy between lattice gauge theory and statistical mechanics. But then the bulk of what I'll talk about is how we do it, how our collaboration generates results, predictions, simulation, theory results at high temperature. So a lot of what I'm talking about is not QCD at low temperature, but QCD at really high temperature. We've got two different results that I'm going to talk about. Our collaboration's got many, many results. I've just taken those two results because it leads nicely into this last topic, which is some work I'm doing with people in Adelaide, Derek Lineweber and others. And that's the thing that's been getting me very excited recently. So let's move to the QCD phase diagram. So this actually is not QCD, this is water. So the humble H2O molecule has this amazingly complex phase diagram. So gas here, liquid here, but these 12 different sorts of solid ice have been known to exist experimentally. Some are theoretically understood, I understand, but not all of them. So even something simple like H2O can have a very, very, very rich phase structure. And the same is true of QCD. So here's the phase diagram. So it's temperature vertically and baryon density, or chemical potential, if you like, horizontally. And this very humble Lagrangian with the quarks and gluons interacting somehow produces this very, very rich phase diagram of QCD. Why have I got three elements? Well, the force binding quarks together is string tension is 440-ish MeV, so that's 15 tons in metric units. So that's the force, and yet down here, that force manifests, so you can have confinement. If you raise the temperature, that force becomes weaker, and eventually it becomes so weak that you get deconfinement, so the hadrons melt. So yes, there is really phases in QCD. The confined phase is the one that most people know everything about, but there is this deconfined phase, so it's a quark gluon plasma. And work is done experimentally to study this, so you actually can increase the temperature. The Large Hadron Collider for 3 or 4 weeks every couple of years runs colliding lead nuclei together, and the Allton detector is used to investigate the physics of that. The RIC is the accelerator in Brookhaven Laboratory, which is in New York State. So yeah, a lot of work is being done experimentally, and our task is to try and theoretically understand what's going on. So here is the RIC collider. That's a typical event. Here is the Allton detector. I used to say Alice, but I've been around CERN enough that people say Alice, so I have to say that now. Here is an event. So it's incredible, the multiplicity, incredible how many states, how many tracks you have to track, because you're colliding, in this case, lead nuclei. So hundreds of nucleons colliding, it produces just this huge plethora of tracks coming up. Just amazing to try and uncover the physics from that. I can talk more about that, but I think time's going to be pushing, so I won't. The motivation, theoretically, is really embodied in the fact that this particle data book, if you get a printed copy, very large number of pages, but no pages, not a single snippet at all on anything to do in this quark gluon plasma. So this phase up here is called the quark gluon plasma phase. So like electromagnetic plasma, you've got positive and negative charges which are moved apart. Here it's the color charges which are moved apart. They're separated, they're not bound together. So in the particle data book, nothing is written about the quark gluon plasma. Okay, so to me that means it's a very, very attractive area to study because not much is known about it. So you can often be amongst the first people to make interesting and useful predictions. And I like that. Okay, so we've got these two contrasting phases, the confined phase and the deconfined phase. So in the confined phase, that's the kind of the phase appropriate at low temperatures and at low densities. So clearly quarks are confined. You can get very accurate predictions, easily less than 5%. So things are bound. So it's a bit like atomic physics, where the nucleus and the electrons bound together. So you get different excited states, but it's sort of bound physics, bound states. The fundamental properties, the things that you end up at the end of your calculation, are typically things like masses or transition components. And the asymptotic physical states are definitely hadrons, they're not quarks and gluons. To get your eye in, as it were, in the quark gluon plasma phase, so that exists at large temperature or chemical potential, everything's upside down. So deconfined, it's like the Wild West. Predictions within 20% can be fantastic. It's a plasma phase, so the sorts of fundamental properties are no longer masses because they're not bound states of hadrons anymore, but more bulk properties like pressures and transport coefficients, entropy densities and so on. They're the appropriate quantities and appropriate terminologies to use. And the asymptotic states, yeah, they're quarks and gluons. Okay, so let's now set the scene for lattice gauge theory. Okay, so introduce it using the following analogy with the Ising model. So the Ising model, spin up and spin down. So that's the action. Okay, this is the sum over nearest neighbours, states I and J, nearest neighbours. And if you want to measure something, then you've got the usual Boltzmann weight, and that's just the stat-mech partition function that you know and love, and you would have done in undergraduate honours year or whatever. Okay, that's the Ising model, simplest sort of statistical mechanics system. QCD looks quite different. The action is like this. So it's a space-time integral. You've got that, but there's kind of nearest neighbour-ish interactions going on there. Here is the path integral now. It looks like that, kind of a bit like that, but not very much. But now we're going to discretize QCD. So we're going to discretize the Lagrangian and the path integral. And we do that by, every time you see a derivative, you replace it by a finite difference. Every time you see a functional integral, you replace it by a sum. Every time you see integral, you replace it by a sum. A function integral is replaced by a sum over configurations. So this little thing on the very top right, which is not, can I make that smaller?
Remove it.
No, anyway, it doesn't matter.
I'm not sure you can actually get in the way that this is.
We can guess what's being hidden anyway. So when we do that, this is what an engineer would do if they're trying to solve stress issues when they're building skyscrapers or buildings. You put on a finite element, finite box. That's all we're doing. We're just discretizing. Once we do that, we can see this is a sum over space-time. That's a sum, and its nearest neighbors, just like that. Here is a sum over configurations, just like this, sum over gluon configurations in this case. So there's a really, really close analogy mathematically between statistical mechanics and lattice QCD. So all the ideas of statistical mechanics can be taken and copied and applied to lattice QCD. So yeah, we're doing, we're approximating our huge infinite dimensional function integral by snapshots of the vacuum, lots of different configurations of generalized Ising spins, basically. And just as we do in that, okay, sorry, just to prove the point, here is a simulation that Derek did, Derek Lineweber in Adelaide. So here, if I press play, hopefully you'll see this is the movie. So the time that you see in the movie is the time in the space-time simulation. So that is one configuration, and what's shown there is surfaces of constant action density. Okay, so that's one snapshot of the vacuum. That's like one configuration. It's 4 dimensions, hence there's a moving time there being shown. Okay, and that's one. If you have 100 or 1,000 of them, that's enough to represent the QCD vacuum, and then you can go and make your measurements on that, just as you do with the Ising model. Okay, and the idea is that you generate those configurations with the Boltzmann weight, and then everything's okay. So to push the analogy with StatMech further, in the Ising model case, typically you're looking at correlation functions. So if that spin is up there, is the spin at a different space-time point? Is it up or not? Is it correlated or not? How does a correlation function vary with distance, exponentially, power law, who knows? Okay, so that's what we do as well. So we look at correlation functions, but I've kind of generalized degrees of freedom. Here, it's in this case, it's a axial vector meson. So we kind of create that system there and we annihilate it there. Okay? And that's our correlation function. And with a little bit of maths, you can see, I haven't gone through all the steps, what you get is a sum of all possible states with those quantum numbers. So if you like, not just the ground state, but all the states I with those quantum numbers. And because we're in Euclidean time, they decay with a real exponent. And at large time, the higher mass states will decay away and you're left with the ground state. And that's exactly what you see here. This is the correlation function, the 2-point function. It's on a log scale. At large times, it's a straight line because it has to be. At small time, it bends away. And this is the effect of the higher states which come in the sum, but whose mass is larger, and therefore numerically, the contribution for those states decays away very rapidly, and you're left with the large time behavior, which is the ground state. So basically, just the gradient of that, that's your mass. So that's the mass of the axial vector. You put the appropriate operators for a proton, so 3 quark propagators, three quark operators with the right quantum numbers, that will give you a similar correlation function. Reading that off would give the mass of the proton. Okay, so that's kind of a summary of lattice gauge theory. It's a story of looking at correlation functions. And this is a really quick snapshot just to show you that it works. This is not our work, this is work done by this other collaboration. These are predictions over here and these are experimental measurements. And I really don't want you to look at this too much, but basically they kind of agree quite well. Okay? So that's the only story that I want you to take from that. So does that mean we now can solve QCD? Well, ish. So not exactly. So it basically solves a QCD version relevant to the parameters that you are putting in your action. So we typically only have 100 or 1,000 snapshots of the vacuum. So our numbers of states in our ensemble, it should be infinite, but it's not. It's much smaller. We would like that to go to infinity. Our lattice spacing, is a tenth of a Fermi or less. That should go to 0, et cetera, et cetera. So all these things are not quite what they want, what they should be. They should be extrapolated away. But there's lots of understanding about how those extrapolations work, the functional form of those extrapolations. And crucially, there is no roadblock between where we're at and where we need to go. We know how to do the extrapolations. Okay, so it's not like it's a perturbation theory where there's a radius of convergence issue beyond which we can't go. That doesn't exist. So basically, the propaganda that I have to say as a card-carrying member of the lattice QCD community is that it's systematically improvable. Okay? So it's QCD, but not as we know it, but we can make it using these extrapolations to be QCD of nature. Okay, so that's great. I haven't introduced temperature yet. With all the work that I'm going to show you, our simulations, our results using a finite temperature. So how do we do this? Well, here's our box. This, if you like, are the three kind of quarks schematically put on that box. How do we increase the temperature? Well, they're two spatial directions, and that's a tau there. It's a temporal direction, the Euclidean time. What we do, surprisingly, is we shrink that dimension down to a smaller distance. In this case, it shrunk hugely, but we have periodic boundary conditions. So both those sites are associated with each other. Okay. So what's going on there? Well, that means that our partition function or path integral in lattice QCD, we make no distinction between the two. Because there's periodic boundary conditions, if you like, it's giving a time translation operator, the e to the Hamiltonian times time. You're doing the translation operator around in time, but you're coming back on itself. Coming back on itself means you're going to do trace that state and that state are the same. And you look at that and you think, well, hang on, the partition function is just like all the bolts and weights for each state I. Okay, and so that look incredibly similar. They're identical if you just associate the length in the temporal direction with one on the temperature. Okay, so the only thing you need to take away from this slide is that. Okay? To increase the temperature, you decrease the temporal extent. So that's our thermometer dial. We can change that dial and make any temperature within reason that we want. Okay, by making it shorter in the temporal direction, we can make it hotter. So that now explains how we can study lattice gauge theory at non-zero temperature. Okay. So as I said, that's what we need to do. Now, there's a couple of ways of doing that. You can vary the scale. So as we go forward in these slides, you'll see the thermometer going higher. We do that by reducing this temporal extent. Over here, we're making the lattice spacing go smaller. But of course, you can make the lattice spacing smaller or the number of temporal sites smaller. Both ways will give you a larger temperature. So you can see that's what we're doing. Two different approaches. We actually use the fixed scale approach, which means we're throwing away data points and trying to get a correlation function using a smaller and smaller number of data points. Okay, that's a problem. Okay, here though, the whole volume shrinks, so you've got finite volume effects. So that's a problem. So two different approaches, both have their problems. For this seminar, I won't go into the details of that any more than that. But yeah, we have to be aware of our systematic effects. Okay, but anyway, we're making our temporal extent smaller to increase the temperature. So the other thing to say is before I talk about the different parameters that we have and how we weren't really solving real QCD, we're solving approximate. Our version of QCD, most of the data I'm going to show you is our so-called generation 2L. And that has a pion mass, not the one that we want, but 100 MeV heavier than the one we want. Okay, so there's technical reasons why that happens, why we do that. It's easier to solve. It costs less taxpayers' money for the computer time. Okay, but that has to be borne in mind as well. And so let me show you some results. Okay, so remember the story of lattice gauge theory is a story of studying correlation functions. So here are some correlation functions. They're on the log plot. Okay, and there's 4 different channels: the D meson, and the D star, and the DS, and the DS star. Okay, so charmed mesons, and you can see the different colors refer to the different temperatures. Okay, the one with the longest extent is the coolest temperature, and then the red is getting warmer, and green and so on, and then this one here is the hottest temperature. Okay, so we thought that they should decay exponentially, so it should be a straight line. Clearly it kicks back up. Have I lied? Well, no, it turns out that for mesons, the way the mathematics work, you can get a so-called forward moving state, but you can switch the time over and you get a backward moving state as well. They're equally valid. So you get 2 states propagating, one forward, one backwards. And for mesons, they're absolutely degenerate. And so really what we have is 2 exponentials back to back. So it's like a cosh. Okay, so that's basically what we have. And so we can pull off here the masses at 0 temperature. And you can see that we get them fairly close. Okay, that's just, this table is just there to show you that we get them reasonably close. We haven't done any extrapolations to infinite volume or to zero lattice spacing. So we're not going to push that very much. Other people do a much better job. Okay. We, though, are really concentrating on doing the studies at non-zero temperature. Okay? So let's look at how we do that. So we need to try and uncover, go back a slide, try and uncover temperature effects in these correlation functions. Okay. So now is this a data analysis trick? What we do is we take our assumed model for how that behaves, how the correlation functions behave. So remember, it was a cosh because it's a forward moving and a backward moving one. Okay. Now we're going to imagine that the mass of the forward and backward movers is obtained at a particular reference temperature T0. Okay, but we're going to assume that that mass is not a function of temperature. So for a different temperature T, we also have the same mass at that initial reference temperature T0. Okay, and so that is our kind of baseline approximation. Now it won't be that, okay, because there's going to be variations on this approximation. But let's divide our actual lattice data by that baseline model. Okay, now this won't be exactly a constant, presumably, because as you change the temperature here, the mass from the data that you're looking at, which is a different temperature, won't be the same as the mass at the baseline temperature, and yet we've assumed it should be. Okay, that's one reason why it's going to be different to a constant. And the second reason is we've only put in one state here, the ground state. What about the first, second, third, fourth excited states? Okay, they all should be there as well. So they're going to spoil that being a constant as well. But as we change temperatures, we might imagine that those higher states more or less contribute in a similar kind of way. So therefore, what we do is we take this ratio with the same ratio, but evaluate at the reference temperature. Okay. That's all I'm going to say about that, because it's just taking ratios to try and cancel out systematics. That's all we're doing. Okay. So if you just take that at face value, here's that same bottom line ratio. Okay. So the R ratio of ratios, and what we're plotting is this ratio of ratios. So on the left are the cool temperatures, less than 127 MeV. The ones on the right is the lukewarm, warmish temperatures. On the left, we can see basically the data is saying it's 1. That's saying that there's no temperature effects. So in other words, the approximation that the temperature at this reference temperature T0 is fixed and does not change with temperature in this range is a good approximation. So the masses don't change with temperature, but up here, stuff happens. It's no longer one. So clearly there's stuff going on there, there's thermal effects going on there. Okay, so where does this change in behavior happen? Well, it happens at about this temperature here, the conventional transition temperature. So there's different masses, the vector in the Euler scale, they become degenerate, roughly speaking, at this conventional transition temperature. Okay, and so that's interesting. So that's one thing that we see from this data. In the D-meson sector, stuff happens at this so-called conventional transition temperature.
Chris, can you just unpack what that is for people who are not lattice or high temperature?
Yeah, so that's a long story which I'll kind of come to, but a good point to raise it now. So initially, this was thought to be the temperature where quarks and gluons became deconfined. Okay, so this was that magic temperature. I won't go all the way back, but in that QCD phase diagram, which separated the confined from the deconfined. Okay, so that's what people initially had in mind. 10 or so. There's a more complicated story which I'll get to. Okay, but it's something like a deconfinement temperature. Okay, so so that was D-mesons. The second thing I was going to talk about is baryons. So lots of work done on baryons, okay, which I won't go into, but surprisingly not much work done in real QCD, real lattice QCD, so that's why we decided to do that. Okay, so baryons. The key thing about baryons is that the nucleon has the positive and negative parity partners. The proton and its n-star partner are not degenerate, nowhere near it. Okay, so just by changing that quantum number, it's very different masses. So that's really interesting physics going on there. But when we increase temperatures, we expect symmetries to be restored. Okay, so perhaps these two states become degenerate, perhaps not. Okay, so that's the idea. So how do we study that? Well, we can study that because we've got this operator and we can introduce a parity operator. So we can literally put this operator of a positive parity state here and have another state here also with a positive parity. So we can literally put in the quantum numbers with positive parity if we want to, okay, and study that. And that's what we do. There is a little bit of interesting maths. It turns out, bottom line, that if you have chiral symmetry, then the positive negative parity states are the same, they're degenerate. So in a universe where the up and the down quarks were zero, the proton and its n-star state, the negative parity partner, would be degenerate if we have exact chiral symmetry. Clearly we don't, but we might expect that they become closer in mass as you increase temperature because things become more symmetric. So we study this, and this is what we get. Here is our correlation function. Again, it's a log plot against time. We've squished all the scalars, so all the different temperatures appear in the same horizontal domain. Why does it look like this? Well, it turns out the positive parity state moves forward in time, but unlike the meson case, the thing that moves backwards in time, I didn't really show you that, is the negative parity state. So when you study one correlation function, you get 2 for the price of 1. The positive parity is the correlation function going forward. The negative parity is the one coming back at you in time. So clearly the red looks like it's quite symmetric, which clearly is telling you that the positive and negative parity states are pretty much the same mass. At very low temperatures down here, they're not the same. That's what we see in everyday life, okay? The n-star is different in mass. We can carry out some fancy maths by taking the difference between the forward and the backward mover. It's a way of numerically studying whether they're symmetric or not, rather than just looking by eye. And when you do that, you get this behavior. And I won't go through it because I'm running short of time. When this ratio is near 1, that's saying that the two states are non-degenerate. When it gets to 0, way down here, they are degenerate. So you'll never get full degeneracy because the quarks always have a non-zero mass. But nevertheless, you have some inflection point. It's like an order parameter. And it turns out, somewhat surprisingly, this inflection point for all these different states occurs also at the same conventional transition temperature. Okay, so it seems that everything happens at this conventional transition temperature in terms of the parity doubling, but also in the d mesons as well. I'll just flick through these. These are telling you the same story. Okay, and this is now looks like the same kind of plot, but this is actually starting the chiral condensate. So clearly the chiral condensate, if it's non-zero, that's out here. The ground state it has chiral symmetry broken. If it gets to zero, it's chiral symmetry restored. Okay, so it's finally normalized, but again, you get this point of inflection, and that occurs also at the conventional transition temperature. So everything's happening at the same temperature. Okay, so I've rammed home this conventional temperature, and now I'm going to throw that up in the air. Okay, so I'm now going to talk about center vortices. Lots of people have studied this. So Jeff Greenside and collaborators were amongst the first. So this is a real cool piece of pure mathematics, which has applications to particle physics. Okay, so it turns out that our gluons are best put on the lattice on the links. So that's a little box on a lattice. The quark fields sit there, and the links sit between them, and they carry the gluonic degrees of freedom. And that makes sense because the gluon, if you like, is the force carrier. So it's got to sit between the quarks. And also makes sense because it's a vector field, the gluon field, mu. So it's got to have a direction, so it can point in different directions. Okay, so the gluonic field naturally sits on the lattice between the sites on those bits, on those straight bits, which we call the links. Okay, and it turns out QCD is SU3. Okay, however, we have this gauge degrees of freedom. We can do the gauge transformation without changing physics. So we're allowed to do gauge transformations any way we want. Physics won't change. Let's try and change the gauge in such a way to make these links as close as possible to what's called the center of SU3. And the center of SU3 is just the cube roots of unity. If it was SU4, it would be the quartic roots of unity. Okay, so it's the cube roots of unity, and we can try and try different gauge transformations until we get the one that gets all links as close as possible to that. And what we're doing there is the part that's the Z part, the cube root of unity, we call the center of the link, and the rest turns out to be perturbative, so quite close to the identity. So what we think about, the way of viewing it is we've got this messy gluonic degrees of freedom, but there's a kind of a topological part and there's a perturbative part. Okay, clearly QCD is non-perturbative in its nature, and we've kind of factorized those out. And the hypothesis is that the center part contains the topological and the non-perturbative part. And I'll develop that more as we go on. Okay, so just trivial bits of mathematics. This n thing is -1, 0, +1. And then we're going to study this plaquette, which is a product of all these links around this four-sided square. Most squares are four-sided. And because it's a group, when we multiply them all together, it's still in this cube root of unity, so it's still a Z3 element. Okay, so when we work out the plaquette, it's also either 1 or either plus or minus I 2/3 of pi. So it's one of those three numbers. Okay, so let's take a step back. What we've done, we've kind of gauge transformed, and then we're going to factorize, and we're going to pull out the Z. And the Z is going to sit on each link, and the Z is one of these three cube roots of unity. So from this point onwards, we're only going to talk about the center elements, the cube root of unity. Okay, so the perturbative part, we're going to let someone else worry about in the future. We're not going to talk about it anymore. And so basically, on each link is either a -1, a +1, or a 0. A bit like an Ising model. Yeah. And when we work out the plaquette, we also get the same thing. The plaquette is either -1, +1, or 0. Okay. Plaquette is crucial because that actually is the lattice version of the action. So the plaquette is the local action. Okay, so we've got these plaquettes. It's either pierced by a +1 or pierced by a -1 or not pierced at all. Okay, and it turns out through like a Gauss's law that you have a conservation. So if the plaquette over here is pierced, that thing, which I'm going to now call a vortex, has to exit this cube. So here it's going out that way. So it means that these vortex lines, these piercings of the plaquettes, go through space-time and they never end. In the Gauss's law, they never end. So this is a picture of a strangler fig in God's own Queensland somewhere. Yeah, so they never end like that. Okay, but because it's always done modulo 3, because it's Z3, mathematically it is allowed for you to have 3 vortices being pierced, 3 plaquettes being pierced by vortices in the same cube. So that is allowed. So you get kind of branching points. That's allowed, but at no point does the chain ever end. Okay, so chains have got no end. So in your mind's eye, all this complicated gluonic degrees of freedom is just lots of chains of these vortices with no ends, which can join. Okay, so that's what it looks like. So lots of lines of plaquettes, you can't really see them. Okay, that's on a 32 cubed by 64 lattice. That's probably one particular time slice of that because I can't show you 4 dimensions. So now we've got to check a few things. We've got to check that that everything's going okay. So I have to now admit the fact that our lattices are anisotropic. So our lattice facing the temporal direction is shorter than the one spatial direction. Okay, which means there's 2 different sorts of plaquettes. The square ones, which are the space-based ones, and the rectangular ones, which are space-time. Okay, we should check the number of piercings per unit physical area is fixed, is the same. And there's no bias. And that's the case. Okay, the red and the blue count the density of piercings per unit area in physical units, the space or space-time pretty much. Okay. So that's a good sign. And you'll see that I've got the horizontal axis in terms of this TC, this conventional transition that I've gone on about a lot. And at first sight, looks like nothing happens there, but if you look closely, there is a glitch.
Sorry, can I ask a stupid question here, maybe? So if you go back to your plaquette description, so if it's not square, so if it's not isotropic, so how do you ensure gauge invariance?
It still is all gauge invariance. So gauge invariance is the action is the trace of the plaquette, and the plaquette can be square or rectangular, and it doesn't spoil gauge invariance. So if you like, it's just the action is sum over all plaquettes, and the plaquettes can be the square plaquettes, or they can be the rectangular plaquettes, and you just have to work out the trace of the plaquette for each of those, or every single plaquette, and then sum them up. And so the gauge invariance is maintained because if you go around a closed loop, the mathematics works out that you do get gauge invariance.
All right. Okay. Thank you.
Yeah. I am conscious that I'm short of time. So here, that green box there is shown here, and there is this orderish parameter change. And if you fit that, you get also our conventional transition temperature being seen in this glitch here, but there's a second transition temperature, very big effect, okay? A new transition temperature. Okay, you can do the same thing with the branching points as well. So you can think about how many branching points are there for unit 3 volume, the branching points where you've got 3 vortex lines coming in together. So there's also a glitch here, right at the conventional transition temperature, but also something going on here at another transition temperature. And you want me to stop after 40 minutes?
No, you can keep going.
A bit more, yep. So looks like there's 2 transition temperatures. Now let's look at the actual visualizations to see what's going on, see if we can glean something from that. So this is now visualizations where we are showing the 3 dimensions, which are space, 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 okay? So we fix one particular time, so we're not showing any variations in time. The 3 dimensions where we are showing projected onto a flat screen are the space-based dimensions. This is coolish temperature, and this is hotter temperature, much hotter temperature. Okay, they look difficult to see the difference between them. But when you slice it differently and show on the screen now the space-time projection, okay, so you're fixing one space, which you're not showing the other 3 dimensions. On the left is the cooler one, and the right is the hotter one. Gee, they look really different, okay? So we manifest in the actual visualizations by eye, you can really see, okay? Now you might be concerned here, that is the temporal direction. The axis is temporal. There's 64 units there. There's only 8 here. So are we seeing a big mess there because we're seeing lots of densities because it's much bigger, just thicker, okay? It's more opaque because it's just more depth. Well, now we've just sliced through the original on the left and just picked a random chunk of 8 units, so it's cropped. It's definitely more density on the left, okay? The blue, by convention in our simulations, is the color given to the largest cluster. So when you look at all these vortex lines, okay, there's some small ones, okay, and then they come in different sizes. The one that's the biggest size we color blue, okay. So very different between the two. Okay, so we can actually make a connection with the confinement mechanism. Okay, so the one on the left, the blue, which is the biggest cluster, clearly what we say percolates. Okay, so it covers and expands out across the entire volume. Okay, so with confinement, how do you measure confinement? Well, there's a well-known method to measure confinement, which is looking at the Wilson loop, which is looking at this rectangle, where one of the axes is in the temporal direction, and counting the number of these vortices which go through that rectangle. On the left, there is a huge number, it's not 0. On the right, there is a tiny number, it's close to 0. You can show mathematically that when this number going through that Wilson loop is non-zero, that shows you've got confinement. Okay, so manifest here is the confinement mechanism happening. Okay, this has been known for some time, but we kind of reproduce those results. So somehow, though, there's when you reduce the numbers of lattice sites in the temporal direction, surely you are not as able to generate as many different configurations like this. Okay, so somehow the key thing is a multiplicity of states, where when you've got a smaller number, you've got less sites to enable you to generate lots of different states. When you've got a large number of sites, you've got a much larger number of sites to make this chain, and therefore the multiplicity of states is much, much larger there. So no wonder you get something which is more complicated in the case where you've got a larger number of sites in the temporal direction. Okay, so I'm going to jump through a little bit and just talk about the cluster extent. Okay, so again, we're talking about percolation. So the blue is the largest cluster. Now, a useful measure is to ask the question, is our blue cluster, our largest cluster, is it as big as it can be? So the quantity we consider then is you take the largest cluster and you work out the biggest distance between any 2 points, which are members of that cluster. So clearly, with periodic boundary conditions, it's a half this diagonal L max, okay? So with periodic boundary conditions, that's as far apart as you can get from any other point on the lattice, okay? So it's a half L max. So if you've got percolation, then this normalized cluster extent should be 1. So the cluster extent, the biggest distance between any 2 points on a cluster, is the biggest distance you can have in your actual lattice. And here's the results. So for low temperatures, it's 1, 1, 1, 1. In other words, you have percolation. Yeah. And then at a larger temperature, stuff happens. Okay. So again, looking at how big these the cluster extent is, and measuring it relative to the biggest the kind of percolation size, you get the same concept that something magical happens here. Okay? So not there, but way out here. Okay, so to kind of nearly summarize, we've got lots of evidence that in fact we've got two sorts of transition temperatures. The conventional one, okay, that Bruce was asking about before, which used to always be the deconfining temperature, so T for confinement. But we see evidence of a second transition, which is nearly twice as high. Okay, and we're seeing that in the center vortices. And the center vortices are things which we believe carry the confinement mechanism. So that's a really important thing. It's like there's a second transition in QCD. So this really virtually is the last slide. I'll make it the second last slide, actually. So what is this TC, this original TC? Well, ironically, people used to think it was a critical temperature, critical in the sense that there was a second order phase transition. Okay, if you remember your stat mech, C for critical, second order phase transition. That's what I originally thought. It turns out that for the quark masses we have in nature, it's not a second order. So then it was called the confinement, TC, ironically, the same first letter. It was thought that that's where you went from a confined to deconfined phase. Okay, but in fact, that's not the case because the string tension turns out to be non-zero above that. And we see some hadrons still being bound states above this TC. And then we think it's the chiral one. So it's where the chiral symmetry is restored. If you like, the chiral condensate gets to zero. And that does seem to be the case. Okay? So this TC now is the same TC, but in fact, it's where you have chiral symmetry being restored. And in this talk, I've kind of talked about it as the conventional, also C for conventional transition. So here's this proposed sort of phase diagram now, where we've got temperature on the horizontal axis. Okay, and here on the vertical axis is the quark mass. Now, experimental physicists obviously can't tweak the parameter, which is the U and the D quark mass. Okay, I don't think you can. No. So lattice gauge theorists can. Okay, we can make it all the way up to infinity. When we make it infinity, it makes our simulations much easier to run. Needless to say, being lazy, they were the first ones done. And so there was a TC up here, 280 MeV. That was well known. Okay. Then we did simulations, so-called dynamical simulations, away from the principal approximation with a moderate to low quark mass. And we saw a transition happening here. And we called that TC, and we called this TC. And we assumed that they were the same. Okay. And that is the conventional picture. What we are seeing is that perhaps this quench transition is the second transition because it happens pretty much at the same temperature. And what we're seeing here in this dynamical simulations that everyone thought was the same as that is an opening up of a new intermediate phase of QCD. Okay, so here is the phase we live in. So it's confined and it's chirally broken. Here, this C stands for chiral symmetry restoration. So you get a chirally symmetric phase in here. Okay, so chiral symmetry has changed between here and here, but it still seems confined. Some hadrons still are confined, are bound. And then above here, it really is the full quark gluon plasma. It's the real thing with the quarks and the gluons being deconfined. Okay, so this is what our results seem to suggest. Lots of what some other people have been pushing an idea of a new phase as well. So we're certainly not the first people to talk about this new phase, but our results, we can pin down these two temperatures very, very accurately, and much more accurately than other people can. And so that is all I will talk about. So yeah, talked about the phase diagram, lattice approach, talked about these two simulations we did, these two quantities we studied to introduce this conventional transition temperature, then introduced center vortices and pointed that there was perhaps yet more richness in the QCD phase than we first thought, and the potential of having an intermediate phase of QCD. Thank you.
Okay. Questions? Archel.
Yeah, thank you, Chris. This is quite unusual for me to see this phase diagram which you showed. The second transition.
Yeah.
So what's going on is that the chiral symmetry is broken, then it's restored, and then it's broken again.
Sorry, that's a typo. I'm so sorry. That's a cut and paste error.
Okay, so
I was going to ask that question myself because I thought just a memo.
Right. The question then is that which chiral symmetry we are talking about? Is that the non-abelian part or abelian? What happens with a U1A?
Okay, so I'm not going to go into the UA1 discussion, but I would say it's a psi bar psi being
Psi bar psi,
yeah,
not at Hooft vertex.
Yes, that's
a psi bar psi going to 0. Yeah. And another thing, you talked about the psi bar psi is how many flavors you
Yeah, so it's 2 plus 1 flavor. So way back here, I showed the psi bar psi plot, which is about here. So this is without data. So it's two light flavors, the U and D, the degenerate, and one strange quark mass. What's shown here is 2 sets of data. So they differ in that the 2 light flavors are different. So the green, the blue one has got a pion mass of nearly 400 MeV, and the green one has got a pion mass of 240, 230 MeV. So 2 different simulations with different masses. Yeah.
Chris, I assume it's easier to do with one flavor, right? What's the result with one flavor? Because then the U1A is the same. What happened?
This side would be the light flavors, the 2 light flavors.
Yeah, but if I consider one flavor and simulate, one flavor QCD. Okay,
so with one flavor QCD, it's quite difficult to simulate, and there are issues with that. That's a whole other seminar. I'm not an expert on that, but with depending upon whether you use Wilson or Stargate fermions, there could be issues with that. So typically, what we do is we have an even number of flavors, 2 light flavors, and then those issues certainly are reduced. Yeah.
Yeah. Thank you,
Chris. You used the 2+1 language there. For the younger students, can you just expand on how flavors are handled in lattice and?
Yes. So,
perhaps at the 1 minute level.
Yeah, at the 1 minute level. Yep. Don't worry. I will. This is what I want to do. Okay. Yep. So there's lots of different parameters, if you like, in the QCD Lagrangian. The one that we're concentrating on now is the numbers of dynamical quark flavors. So literally that means the quarks that appear as quark anti-quark loops in the vacuum, if you like. So it's a QQ bar loop. Now those QQ bars should be allowed to be any quark that exists in nature. So it should be UD, S, D, T, and B. Okay. But that's a lot for a lattice gauge series to simulate. Okay. Clearly the ones which are heavier will have less effect because their mass means they're not produced often, so they're not going to have so much an effect. But it's the lightest ones that we need to home in on. And so if you want to do a serious lattice QCD simulation, you've got to at least have the 2 light ones, the U and the D. So that means you really do have, in terms of Feynman diagram language, U and D quarks, U and U bar, quark anti-quark pairs being produced, and that would be the 2 light flavors. We do 2+1, which means we have those 2 light flavors, the U and the D, and we also have a strange as well. Okay, so we can change the mass to be anything we want. The strange one we tune to be exactly the strange quark mass, give or take. The light one we try and get as light as possible. It becomes increasingly more expensive to make it as light as possible. So we compromise and have it light-ish, but not as light as it is in nature. Yeah, more than a minute, but yeah.
I mean, you want to sort of push as many of these numbers to the right as possible. Like, just in terms of like computing resources, how do things scale with these numbers? Is it like
really good? Yeah,
linear and F or what?
No. This one is linear in n, but the error bar goes as 1 unwritten. This is really statistical. So it really is a sampling question. If you've got 4 times as many samples of a number, you've got twice as good statistical error. It is like undergraduate laboratory experimental physics. This one very much is nonlinear, and it might be if it kind of all hell breaks loose if you go very fine, because you might get stuck in some topological phase, a different topology to what I've been talking about. So this one you might hit a brick wall algorithmically. This one has been amazing advancements made in algorithms to push this lighter and lighter. And now the serious lattice gauge people who are doing zero temperature work actually run at the physical UND quark mass, because they've got some fantastic algorithms which you can deal with this. The problem is when you get lighter and lighter, you're basically inverting the Dirac matrix, which becomes singular. So at the chiral limit, it's a singular matrix. At the UND quark mass from nature, it's pretty bloody close to singular. Okay, so but there's some fantastic algorithms to get there. This isn't linear either, because it's L to the 4th really. So it's not far off linear in L to the 4th. And here, this is really just is just what I've said here repeated by the number of flavors you have. But putting in Charman is really cheap to do. Putting in Strange is fairly cheap. Putting UND is not cheap. Yeah.
Are there questions on Zoom?
No one's raised their hand, but
Okay, so other questions from the room?
Like, I wanted to ask, like, how do you know that the vortices are related to the confinement?
Yeah. So it really, I've skated over this, but this thing with the oblique kind of rectangles is the nub of it. So it will get there in a second. Yeah. So it is, this thing here represents a Wilson loop. So basically you take a trace of all the links multiplied together around the Wilson loop. And you can show that that is the same as counting the number of times that rectangle has been pierced by one of these vortices. Okay, so mathematically you can actually show that. Okay, so again, I want to stress that everything I'm talking about here isn't the full QCD, it's just the factorized QCD, where we're just looking at the factor, which is just purely the set of vortices. Okay, so in that case, if you were to work out the Wilson loop, it really just is counting the number of piercings that there are. Okay, in the full QCD, you'd have to do a bit more complicated calculation, but it still is just multiplying all the links around and taking the trace, and that is it. Okay, and here you can see it's going to be non-zero. Here you can see it is going to be 0, and that turns out to be confinement, and that turns out to be not confinement. I can say one more thing, which actually be a lot more useful than what I've said probably, and that is that this basically is e to the minus free energy for a single quark, because it turns out that this also measures the free energy of a quark, or e to the minus of free energy. Okay, if I got this right. So if the free energy is infinite, that means it's impossible to create a free quark. And so you must be that one there. So it's non-zero. We said that the wrong way. But if it's possible to create a free quark, then it turns out that that value is 0. I haven't explained that, but it's also called the area law. So it's like putting a quark and an anti-quark there and propagating that state forward in time. And if it is goes as e to the area, then that's like saying the area is like the distance between the two times the time, and that will then say that the energy of those two states increases linearly with that dimension. It literally is, the area of a rectangle, length times breadth. One of those lengths is the distance between the two. And this Wilson loop therefore measuring the energy, which increases linearly with the distance between the quarks. So you've got a non-zero string tension. If I had a blackboard, I could write that.
Like so basically, if you don't have vortices, you can have zero mass for the quark, right?
You can have the possibility of having a free quark here. So where you've got no confinement, it's possible to have a free quark in this phase. That's right.
Okay. And do you also, can you see this phase transition in another observable besides the number of vortices like this?
Yes. So it depends which phase transition.
Like the new one, you are like the confinement
one. No. So thus far, I don't know of any, but this is very new work, and so we need to look at that and to see whether anyone's seen hints of this happening at other transition temperatures. Actually, I tell a lie. The two papers I mentioned at the end, some of those, the two papers I said at the end, which also propose a second phase transition, have looked at lattice data, and they see some hints of that using their data, but I'm not aware of the details of that. Yeah.
Maybe take one more question.
Yeah. Just off what you're talking about here, in this non-confining phase,
Yeah.
it's not strictly zero, right? It's like do you actually see this, the length, whatever the actual?
Yeah. So it's not strictly zero, but one might imagine that if you take all those extrapolated limits, so take the lattice spacing going to zero and take the infinite volume limit, then you might expect it literally to go to literally zero. So it's like stat mech when you're trying to look at a critical transition. In the continuum and infinite volume thermodynamic limit, things will become singular, which means they blow up to infinity. But if you're starting on a finite box with a finite number of degrees of freedom, you won't be able to generate an infinity. So you'll be able to generate something which peaks up hugely, but not be infinite. And so in the continuum limit, infinite volume limit, yeah, I think it will be really zero.
But my Wilson loop doesn't. I'm not very familiar with Wilson loop. That should be not zero, shouldn't it be the?
Remember, you got to.
I get a different scaling.
You got to keep the Wilson loop the same size in physical units. So to reduce the lattice spacing, the number of lattice sites that it spans increases in concert.
Okay.
Yeah.
One more.
Just a very quick question. With this, the plaquettes, is this independent of the quarks? Like, is this just a free gauge theory? Or?
Yeah, so that's a good question. So in fact, I didn't have time to explain that. This is a dynamical simulation, but all you're seeing here is the gluonic component of it. But through the miracles of Grassmann algebra, you can actually do the functional integral part over the fermion degrees of freedom. And the expense you pay is that it generates of the gluonic matrix. So sounds like I'm having it both ways. So only gluons are being generated dynamically, but because you're including that ugly determinant, that determinant actually came from the Grassmann, from the fermionic degrees of freedom. So you really are including the fermions, but they're somehow embodied into the gluons.
I see.
Yeah.
We sometimes end the recording at this sort of point and then allow extra questions.